Hello, this is Mr. Mack. I'd like to talk to you today about limits. Now, limits are really the foundation upon which all of calculus is built, and it's important for us to understand this foundation. So let's start out. The basic concept of limit is that we ask what happens to the value of a function as x gets closer and closer to some constant. Now, think of the value as the output of the function, and think of x as the input of the function. So what happens to the output of a function as the thing we're putting in, the input, gets closer and closer to some constant? We ordinarily refer to that as c. Now, the symbol looks something like this. The limit as x approaches c of f of x is equal to L, where L is the limit. Now, we don't actually look at the value of f of c. We just look at the values as we approach c from both sides for the input and what the output value is. So let's take a look at a simple function. Let's let f of x be equal to x plus 2. And we're going to ask, what is the limit as x approaches 3 of f of x? Well, we could start out by saying, all right, well, we'll see what the value is of the function at 2. And obviously, f of 2 is 4. And then we'll start getting closer and closer to 3. We'll try 2.5, and we get 4.5. 2.9, we get 4.9. 2.99, we get 4.99. And we could keep this up, 2.999, we get 4.999. Now, we're not actually going to look at 3, but we do have to look at it from the other side as well. So let's start at 4 and work down. F of 4 is 6. F of 3.5 would be 5.5. F of 3.1 is 5.1. 3.01, we get 5.01. 3.0001, we get 5.0001. So as you can see, from both sides, as we squeeze in on an input of 3, the output squeezes in on an input of 5. So we say the limit as x approaches 3 of f of x is 5. Now, let's take a look at a picture. It's always a good idea to take a look at a picture of f of x. Now, obviously, f of x is equal to x plus 2. And notice what we've got here is the line y is equal to x plus 2. And what we're looking at is this value of 3 here. Now, notice if we actually went up to the function and across, the output would be 5. But you see, we're not really interested, or we don't really want to look there, because sometimes that particular point doesn't exist, but we can still have a limit. And that's what makes calculus works. So as we get closer and closer to 3 as an input, the function gets closer and closer to this point, and the output gets closer and closer to 5. Now, as we come towards 3, the input from this side, the function comes down towards this point from the right, and that means the value of y approaches 5. And so that's actually what happens there. Now, if we were to change the function a little bit, let's take a look at g of x. And we'll let g of x be a mustachioed function. It's going to be x plus 2, or x not equal to 3, and it's going to be undefined at x equals 3. Now, once again, notice as we approach 3 from the left, the function approaches this particular open circle, and so actually the value is approaching 5 from below. As we approach 3 from the right, the function approaches this open circle, and so the value approaches 5 again. And since we're not actually looking at 3, we determine that the limit as x approaches 3 of g of x is 5. Now, let's try it again. This time, let's let h of x be the mustachioed function x plus 2, x not equal to 3, and 1 if x is equal to 3. Now, here's 3 again, and h of 3 is actually 1, but as we approach 3 from the left, the value is approaching 5 from the left here. And as we approach 3 from the right, the value is approaching 5 from the right. And so again, we would say the limit as h of x, the limit as x approaches 3 of h of x is equal to 5. So what we have here is basically the 3 cases where the limit does exist. On the first one, the limit, didn't write that in here, the limit as x approaches 3 of f of x is equal to 5. The first one is where f of 3 is actually 5. Now, we didn't need that for the limit to exist, but if the function is continuous, then usually that is what the limit will be. In the second case, the limit as x approaches 3 of g of x is 5, but g of 3 is undefined. That doesn't bother us with the limit. We still say the limit as we approach 3 is 5. And then finally, we have a function where the limit as x approaches 3, there should be an arrow there, of h of x is 5, even though h of 3 is a different value, 1. So in all 3 of these cases, the limit is the value that we're squeezing in upon. Now, let me show you an example of a function where the limit doesn't exist at a particular point. So let's take a look at this function, and this is the function, let's see, can I change this? 3, right? Oh, what am I doing? I can do this. 1, 2, 3, there we go. This is going to be the limit, this function, let's call it j of x, is going to be the absolute value of x minus 3 over x minus 3. Now, notice when x is greater than 3, like, let's say if x is 4, we get 1 on the top and 1 on the bottom, which is 1. When x is 5, we get 2 on the top and 2 on the bottom, that's 1. When x is 6, we get 1 on the top and 1 on the bottom. Again, that's 1. So we get this y equals 1 line over here. Now, when j is 0, for example, we get 0 on the top, and or we get 3 on the top and negative 3 on the bottom. That's negative 1. When x is 1, we get negative 2 on the top, 2 on the top and negative 2 on the bottom. That's negative 1. And so we get this line, y is equal to negative 1 over here. Now, at 3, let's see, the limit as x approaches 3 of j of x turns out to not exist. A lot of times we put DNE, does not exist, because as we squeeze in from the right towards 3, the value is 1 or approaches 1, and as we squeeze in from the left to 3 as the input, the value actually approaches negative 1. So therefore, since we're squeezing in on different values as we approach this constant 3 from different sides, then the limit does not exist. Okay, now I'm going to stop this video at this particular point and start another one. We'll call that limits 2, I guess.